when we're looking at pH, what's it based on? What kind of really does pH, what does it stand for? Power of the hydrogen ion, all right? Power of H. That's really what we're looking at. And then these numbers, guys, are directly related to logs of the hydrogen ion concentration, which we'll talk more about. So again, lower the number, the pH number, more acidic, the higher it is, the more basic. So what's happening, guys, and this is just kind of the theory behind it. Remember, these are the best explanations that we have right now for acids and bases. They could change, but they've kind of held for a while now. Basically, guys, what you've got going on here that this picture in this graph shows is that you've got acids that have the hydrogen ion that they're willing to give up. Again, that's by what definition is a hydrogen donor? Acid by Bronsted-Lowry, right? And bases are hydrogen acceptors, right? And that's kind of what's going on. Is when you mix an acid or base with water, you get these ions that are kind of floating around there, all right? Anyway, so down here, if we take a look at what's actually happening, guys, in solutions, so something to actually have a low pH, you have a lot more hydrogen ions than you have hydroxide. So notice you have both of those present in the same solution. Both ions are there. Why? Because, well, water's there, so water's going to break up into those. But for it to be an acid, guys, you have more H plus than you do hydroxide. On the flip side, if it's basic, you have more hydroxide ions present than you do hydrogen ions. All right, so that's kind of what you want to think about that's going on at the particle level. All right, so as we get into some of the calculations here in a little bit, you want to be thinking, does my answer make sense? And this is kind of how you want to think about it. All right, visualize the ions that are in solution. So what's the range of the pH scale? Yep, 0 to 14. pH of acids is going to be 0 to less than 7. All right, I got to think which is the less than sign. That one right there. All right. pH of bases is 7 or greater than 7. So that one right there. Sad that I always got to think about that. What does pH stand for? We already said that's power of H plus. What's the formula, guys, for pH? Yeah, so there's a couple things. All right. One, guys, notice how I wrote concentration. I've got brackets, right? All right, brackets means concentration. It's something that when we did solutions, I don't even think I mentioned really, but we really see it a lot when we talk about acids and bases. So just keep that in mind that brackets equal concentration. That's something that we will see a lot in this unit. Is it possible to have a pH of 15 or negative 2? No. You sure?
You can go below.
Right. Mathematically speaking, guys, it's possible to get a log that value, but are we actually going to see that in terms of actual solutions? No. All right, so for all intents and purposes, we're going to say no, but mathematically, you could potentially get something like that. We're not going to see it, though, with a concentration of a solution. What's that?
Hyperbase.
Hyperbase, and yeah, those crazy. There actually, I think, are super strong acids and bases that could have that nowadays that they've synthesized. So, guys, pH, using the concept of H plus and OH concentration, this is something what I want you to make sure you have down. If something is acidic, okay, your hydrogen ion concentration is greater than your hydroxide ion concentration. Okay, again, brackets means concentration. If something is basic, all right, that means your hydrogen ion concentration is what? Less than your hydroxide. What does it mean if something is neutral then? Yeah, you have equal amounts, equal concentrations. So every solution that you have, all right, you have both of those ions. It just depends which one's more prevalent. So if you don't have this written down, guys, in your notes, I highly recommend you to write this little chart down so that you kind of keep that in the back of your mind. All right, that if something's acidic, you have more hydrogen ions. If something's more basic, you have more hydroxide. If it's neutral, that means you have the same amount of both. And we're going to show that mathematically here. So pH scale, if we're going to draw something out like this, okay, you've got 0 over here, 14 up the top. In the middle is going to be 7. What'd you find for coffee? Yeah, is it strong acidic? No, it's more of like a weak one, guys. So it'd be somewhere around here. We're not going to put actual numerical values with it today. We're just kind of putting it kind of to give you guys an idea of where they might fall. Drain cleaner? Yeah, it's going to be a strong base, guys, somewhere around here. I'm just going to call it Drano. So those are taken care of. Baking soda. Yeah, it's going to be a weak base. I don't know why I was writing weak base. All right, but baking soda. Stomach acid. Yeah, it's going to be a strong one, guys, down here. And it should be strong. If you think about it, you want stomach acid to be so it can break down everything that you eat. Water.
Neutral.
Should be neutral, right? We'll see if it actually is or not. And then milk. It's actually slightly. It's right around. Yeah, it's right around there. All right. What's in milk that might make it slightly acidic? Yeah, lactose, right? Lactic acid. That lactic stuff that's in there. All right. So that's just kind of a recap, guys. How many of you knew pretty much all this already? All right. Maybe the only new thing is just thinking about it in terms of the ions, and that's the point of us kind of introducing it. So we're building upon what you already know here within this unit. We're going to take it a step further. So here we go. We just did this, guys. If the hydrogen ion concentration is greater than hydroxide, what do we have? We have an acid. And if it the other way is true, we have a base, okay? So a neutral solution, guys, is where you have equal amounts of both. Now, notice how we are using things in the scientific notation. How do we plug that into our calculator if we have numbers in scientific notation? Yeah, that E function, remember? We don't have to do a caret key or 10 to whatever power. We would write it, we would type it as 1 E, and then it would just be -7. And make sure, guys, that you look to make sure, are they positive or negative exponents, all right? And typically with these concentrations, they're going to be negative because they're very, very tiny numbers, okay? Very, very tiny numbers. So keep that in mind as we go throughout today. So there are 6 equations that we're going to discuss, and I've got a little sheet for you to have. So our first equation that we're going to discuss, guys, is called the KW formula. All right, KW just means the ionization constant of water. If you look on your gold sheet that I just gave you, this is listed there for you guys because it's a constant. It's not going to change. The KW constant is 1 times 10 to the minus 14. Okay, that's a number that does not change. Is it a big number? No, super, super, super tiny, which is why we're using scientific notation. But guys, basically, when you take the concentration of hydroxide ions in a solution and you multiply them by the hydrogen ion concentration, you always, always, always get to that constant for water. Okay? So again, all the acids and bases that we're looking at are aqueous, meaning that they are based with water as the solvent. If we changed up our solvent, this value might change, but we're not going to worry about that in this class. All right, we're going with just water. So we've got to calculate both the hydrogen ion concentration and the hydroxide ion concentration for this acid. How do I know that this is an acid?
Because the exponent is less than 1, so it's like 4.
You're on the right track. There's part of that, which we'll get into more. But guys, just how do you know that this is an acid? What's it have with it? It's got the H, right? Plus, this is one of the strong ones you need to have memorized. It's nitric acid, so make sure you have those memorized. Oh, I see. You were looking at these two? The hydroxide and the hydrogen? Oh, okay. I'm sorry. I was looking at the example. That's okay. That's on me. All right. It's a Monday. That's on me. HNO3, that's what I was talking about. So, here's our example, guys. We've got to figure out the hydrogen ion and the hydroxide ion concentration. So we know that we're going to use this formula because it has both of them in there. So hydroxide, doesn't matter if I put hydroxide first or hydrogen first. No, because it's multiplication. Okay, so you can switch it up if you want to. So we know that when they are both multiplied together, it equals this constant. Does anybody see the issue that we're going to have here trying to solve this formula? Do we know either of the concentrations? So that means we have two unknowns, right? So where are we going to begin? Well, we need to find both of these, the hydrogen ion and the hydroxide ion concentration. We actually have more information, guys, than it may seem. That kind of goes with that question I was just asking. What do we have here? HNO3 is a what? It's an acid. So, guys, by us knowing that it's an acid, that means the concentration of that solution is going to give us an insight into which of the two ions. Why do you say H plus, Grant? Because it's an acid. And an acid, guys, produces that H plus. It has that with it. So by us just reading this problem, this value right here, that concentration of the solution, since we have an acid, that's our hydrogen ion concentration right away. All right? So our hydrogen ion concentration is going to be 1 times 10 to the minus 4. Okay? What's our unit going to be since it's concentration, do you think? Molar, right? So it's a 1.0 or 1 times 10 to the minus 4th molar solution of nitric acid. So that tells us, guys, that our concentration of hydrogen ion is 1 times 10 to the minus 4. So really what we're looking for is hydroxide. Now before we go ahead and solve this equation, okay, let me just ask you this, guys. A times B equals C. If I said solve for B, what would you do? Yeah, we divide by A from both sides, so we get B equals C over A. This formula is exactly the same way. Okay? This is like saying, I'm going to do it in a different color so you can see it. A times B equals C. It just looks more confusing because, oh, we have brackets and we have hydroxide or hydrogen ion or whatever. And we have a number over here already. Don't get confused, guys. It's your basic algebra like we've done so many times already this year. It just looks a little bit different. So we have the hydrogen ion concentration. We're looking for hydroxide. How do I get hydroxide by itself? Divide by H plus concentration. Those cancel out here. All right. So really it's hydroxide equals 1 times 10 to the minus 14 divided by, what's our value for hydrogen ion? Yeah, 1 times 10 to the minus 4. There you go. Do the math. So our answer here, when you plug it in, is 1 times 10 to the minus 10 molar. So now we have both of our concentrations. If you were to check them and you multiply them together, guys, what do they have to add up to or multiply out to? Right. So you could go back and double check that you did your math correct, because if they both, when you multiply them together, they equal the 1 times 10 to the minus 14, you know you've done it correctly. Is that, when we break it down, is it super bad? Does it look rough when you first saw it? Probably a little bit, yeah. Right? This is something where maybe you haven't done this type of math in a long time, if ever. So it's going to take some practice. All right. So let's take a look, guys, at example number 2. Okay. We're looking for hydrogen ion and hydroxide ion concentration. So when we're asked to solve for both of those, what formula am I going to use? KW formula. So I'm going to write it down. Again, H plus times hydroxide equals 1 times 10 to the minus 14. Again, remember, you don't have to memorize that number. You don't have to memorize these formulas. I'm going to give them to you. I would imagine on your Regents exam, if they ask you to do a problem like this, they're going to give you the formula. If they don't, well, you know how to do the basic ones. Or you will know. So we're looking for H plus, and we're looking for hydroxide. So we have 2 unknowns, but do we really have 2 unknowns? No, right? Because we have a solution given to us. What's the name of my solution here? Calcium hydroxide. Is calcium hydroxide an acid or a base? How do you know it's a base? Hydroxide, right? That's your clue. Just like with acids, guys, you have an H that's starting there, or it's starting with an H. This, you know that hydroxide is going to be a base. So is this my concentration for hydroxide, do you think? What's different about this one than the one we had before? It's not in scientific notation. Okay, that's not a huge deal. What else do you notice that's different about this one? What do you mean it's not 1, it's 2?
If it was in scientific notation, the first number would
Okay, right. So we have a different number. So what that means is, we can't really necessarily do this in our heads, so to say. The other one we could have done in our heads, and you'll see as we go through and do more practice how we could have done that mentally. There's something else, guys, that's different about this one versus this one. Besides that one's an acid and one's a base. Yeah. How many hydrogen ions did we have over here, guys? We had 1, so that made our work a little bit easier. That means our concentration of 1 times 10 to the minus 4 was truly 1 times 10 to the minus 4, because when HNO3 breaks up, we get H plus NO3 minus. So it was a 1-to-1 ratio. Over here, though, when we break this up, we get Ca2 plus 2 hydroxide ions. Okay? So what do you think that's going to do, guys, to our concentration? Yeah, we got to multiply that number by 2 because, for every 1 mole of calcium hydroxide that we really have twice as many hydroxide ions. This is where we start getting to that polyprotic or polybasic, all right, where we have, a monoprotic is 1 ionizable proton. That was that term we talked about last week. Now, guys, we could see di or tri, and we just have to take that into account how many ions are going to be present. So we may have a 0.02 molar solution of calcium hydroxide, but when we isolate out our ion that's present, which is hydroxide, we really have twice as many hydroxide ions per 1 mole of the entire substance. Does that make sense? Okay, because there's 2 ions to balance out that calcium 2 charge. So we got to multiply this by 2. So what's our concentration of hydroxide ion going to be? Yeah, 0.04. All right. Still, that's just one extra step we got to look for. Is there a subscript with my ion or not? If there's a subscript, I multiply the concentration by that subscript. If there's no subscript, then it's just going to be the same number. So we still got our concentration. So now we're just going to plug it in. I want you guys to try to solve for the hydrogen ion concentration using KW. All right? All right, here we go. Let's take a look, guys. I'm going to get hydrogen ion by itself. Divide by the hydroxide from both sides. All right, so H plus concentration is going to be 1 times 10 to the minus 14 divided by 0.04. What do we get then for our hydrogen ion concentration? Hydroxide, hydroxide. What was the exponent? No, you're fine. Yeah. No, I'm sorry. We had the hydroxide. We're looking for hydrogen ion, so it was hydrogen ion, like I had said. We're using the hydroxide to get to it, so I may have misspoke. Negative 13. All right, molar concentration. Now, guys, let's just think. We had a base to start with. Is this a strong or weak base? It's a strong base. Can anybody tell me why it is? Anybody remember from last week? Okay, it's not just that. What makes it a strong base, guys, is remember, if you have a group 1 or 2 metal with hydroxide, those are your strong bases. Transition metals with hydroxide, those are weak bases. That was just one of our things that we had outlined last week with our overall property things, so just keep that in mind. That's why I want to hit on that. Having 2 hydroxides does make it stronger because you have twice as many of those ions in solution. So does our answer make sense? Yes, it should, because hydroxide concentration is much larger than hydrogen ion. So that's the way you can kind of make sense of it all. Did I do it right? Does my answer make sense? Okay. Questions? I want you guys to do the next one that you have right there in your notes. All right, so first off, which ion, guys, do we have information for? Yeah, the H+. How do we know it's H+? Because it's an acid. It's sulfuric acid. What do we have to do with that number, though? Yeah, because this is a diprotic acid. That means there's 2 ionizable protons. We've got to multiply that by 2. So our hydrogen ion concentration is 2 times 10 to the minus 3rd molar. Now, guys, one thing I want to point out, H3O plus and H plus mean the same thing. All right, if you see hydronium ion or hydrogen ion, it's referring to the same thing, meaning it's the acid ion. All right. So then we get, I'm just going to kind of simplify it already. I'm not going to walk through it. OH concentration equals 1 times 10 to the minus 14 divided by 2 times 10 to the minus 3. Our hydroxide ion concentration, when you do that math, should be what?
5 times 10 to the negative 12.
Bam. Just like that. Okay?